The average American household spends approximately $1,100 per year on residential cooling. The meter spins, the compressor cycles on and off through July and August. The bill arrives, and somewhere under the backyard, 6 feet below the surface where the temperature has not changed since January, the soil sits at 55 degrees Fahrenheit and waits for someone to run a pipe through it. A peer-reviewed study from the Indian Institute of Management, Ahmedabad, documented that a single buried pipe cooled incoming air by up to 14 degrees Celsius, with zero electricity input, zero refrigerant, and zero moving parts. The air conditioning industry accounts for 1/5 of total global electricity consumption, according to the International Energy Agency. A $300 pipe eliminates the need for it. This video covers the physics, the 3,000-year history, the building code mechanism that sidelined it, and the exact materials list. 13 minutes. Start the clock. The ground does not behave like the air above it. Air temperature at the surface fluctuates constantly, hourly, daily, seasonally. Ground temperature does not. At depths of 1 to 4 meters, ground temperature is stable, with no diurnal fluctuation and only small seasonal variation, documented in the IIMA working paper from 2004. Temperature waves dampen as they penetrate the soil. Diurnal fluctuations diminish within less than 1 meter of depth. At 3 meters of depth in Ahmedabad, soil temperature fluctuations reduce to just 2.8 degrees Celsius across the entire year. The soil at that depth is a near constant thermal mass. It stabilizes near the annual mean temperature for that location, approximately 55 to 65 degrees Fahrenheit across most of the continental United States, regardless of what the air above it is doing in July. An earth tube exploits this directly. Hot summer air enters one end of a buried pipe. The air contacts the pipe wall. Heat transfers from the air into the surrounding soil. By the time the air exits the other end, it has given up a significant portion of its thermal energy to a heat sink that is effectively infinite and costs now nothing to operate. But the physics does not care about building codes. The ASABE study by D.O. Baxter in 1994 documented an instrumented earth tube system, 64 meters of 15-centimeter diameter corrugated metal pipe, buried 1.8 meters deep, showing promising potential in the cooling mode. In 2003, Girja Sharan and Jadhav Ratan at the Indian Institute of Management, Ahmedabad, published the result that defines this technology for practical purposes. A single-pass earth tube made from a 50-meter pipe of 10-centimeter diameter, buried 3 meters deep, cooled ambient air in May by as much as 14 degrees Celsius. 14 degrees Celsius is 25 degrees Fahrenheit. That is the difference between a 100-degree summer day and a 75-degree room, from one pipe with no electricity, no refrigerant, no compressor, and no monthly bill. The results showed a single pipe could produce that cooling. The system works in reverse in winter. Cold incoming air contacts the warmer soil at depth and exits pre-warmed. The same pipe, the same physics, zero operating cost, running in both directions. This is not theory. It is in a peer-reviewed study from one of India's top engineering institutes. And it is also 3,000 years old. Yazd, Iran, over 40 degrees Celsius in summer, no mechanical air conditioning, ever. UNESCO designated Yazd a World Heritage Site in 2017, in part because its ancient wind catcher and qanat systems remain intact and in active use. The Badjir, the Persian wind catcher, is a tower structure that catches prevailing wind at elevation and channels it downward into a building. Excavations in Sharud, northern Iran, documented by Hijazi and Hijazi in 2014, prove the existence of Badjir structures in Iran as early as 4000 BCE. When combined with the qanat, underground water channels approximately 3,000 years old, the wind catcher system produced something that functions as a direct precursor to the earth tube. Cool air from the underground channel is drawn through the building by the pressure differential created by the wind tower above. Hot air is expelled from the top. The combination produces more than 15 degrees Celsius reduction in air temperature in dry desert climates. Field studies document indoor temperatures of 23 degrees Celsius to 28 degrees Celsius when outside temperatures exceed 40 degrees Celsius. No electricity. This system was in documented active use for over 1,000 years. It did not stop working. A new industry arrived and made it economically invisible. That number, 1/5 of all electricity on Earth, goes to one appliance. And there is a $300 pipe that replaces it. Every home that installs an earth tube reduces its dependence on grid electricity for cooling. Every home that reduces demand is a customer using less of what the utility sells. Building codes in most United States jurisdictions require mechanical ventilation, systems that consume electricity and that fit within regulatory frameworks the mechanical industry helped write. Earth tubes do not fit neatly into those requirements, not because they are unsafe, but because no standardized certification framework exists for them in most American jurisdictions. The absence of a standard is itself a mechanism. A technology without a code pathway cannot be specified by an architect, approved by a building official, or financed as a code-compliant system. A 30-month monitoring campaign on a school building in Imola, Italy, published in Energy Procedia in 2015, used a horizontal earth-to-air heat exchanger with 32 buried pipes and showed consistent cooling performance across the entire monitoring period. The building codes that sidelined this technology were written in a regulatory environment shaped by an industry with 1/5 of global electricity consumption as its revenue base. A basic residential earth tube requires 3 components. First, pipe minimum 10 centimeters in diameter, ideally 15 to 20 centimeters. Use PVC or corrugated metal, both documented in the research literature. Second, burial depth minimum 1.8 meters, ideally 3 meters, where soil fluctuation is only 2.8 degrees Celsius across the year. Third, length minimum 30 meters, with 50 meters to achieve the documented drop of 14 degrees Celsius. Connect the outlet to an intake vent at the home's foundation or basement level. Cooled air circulates by natural convection, using the stack effect. A small low-wattage fan can drive airflow actively if needed, but is not required. Total materials cost is under $300. No moving parts, no maintenance schedule, no service contract, no refrigerant. The pipe does not wear out. The soil does not stop being cool. The average American household spends approximately $1,100 per year on residential cooling. An earth tube installed for $300 eliminates a substantial portion of that permanently. The people of Yazd understood this 4,000 years ago and maintained indoor temperatures of 23 to 28 degrees through summers exceeding 40 degrees, without a single kilowatt of electricity for 1,000 years. The technology was not superseded by something better. It was sidelined by something more profitable, a mechanical system that requires a monthly bill, a service contract, refrigerant that degrades, and a compressor that fails on the hottest day of August. The pipe under the ground asks for none of that. The International Energy Agency's 1/5 of global electricity figure is not a measure of necessity. It is a measure of what happens when a 3,000-year-old passive solution is replaced by one that generates recurring revenue. Drop your current monthly cooling cost in the comments. The people reading those comments are building earth tubes this weekend. Share this video with one person who has opened an electricity bill in July and felt the number was wrong. The next video covers a wall material that outperforms a $2,000 triple glazed window for $15. Same physics, same industry that buried it.